Alright, in this mini lecture I'd like to talk about how to draw the energy diagrams that you'll be asked about on the test. Now first of all, let's look at some general shapes of what the SN2 and SN1s look like. First of all, let's look at SN2, and as we've been talking about, SN2 is a one-step process which is going to have a single hump. The activation energy of that hump will be from the reactants up to the tip of that hump, so that's going to be the highest energy part of the diagram. And then you've got the delta H naught, which is the enthalpy change, which is always going to be between the reactants and the products, no matter what diagram we happen to be looking at. Now, if we're talking about exothermic, it means the products are of lower energy than the reactants because energy got released during the reaction process. So the products are actually more stable because the energy is lower for the products than it is for the reactants. That difference in energy had to go somewhere, and that probably got released as heat. In the case of an endothermic process, the one hump is still here, and you've still got the activation energy being from the reactants to the top of that peak. But now the delta H is going to be between the reactants and the products, and you're actually going to get a positive delta H here because the products are higher energy than the reactants, but the delta H will still be between the reactants and the products, but the products are now of less stable than the reactants actually were. In the case of the SN1 reaction, the hump will be a two-step hump. If it's exothermic, the products again will be lower than the reactants. The delta H will still be between the reactants and the products, and the activation energy will be between the reactants and the highest point of the first step. Now the reason for this is because the activation energy for the second step is really tiny. It goes from here up to here. So this isn't the activation energy for the entire reaction. If it's got enough energy to get over this first hump, it's definitely got enough energy to get over this second hump. So that's why we talk about the first step being the rate determining step, or the step that's going to determine how fast the reaction's going. So we've got the reactants down here, the products are down here because we've got an exothermic process. The products are lower energy than the reactants. In an endothermic process, the products are actually higher energy than the reactants. So what that means is that we're going to have a delta H that still goes from the reactants to the products, but these products are less stable than the reactants were. The same general shape is present for the SN1 diagram, however, and the activation energy still runs from the reactants up to the top of this transition state. Alright, so there's two examples that we'll be looking at. We've got the case of a primary with Cn minus, and in the question you'll be told that it's either an exothermic or an endothermic process, and you will make up your diagram accordingly. This particular one is exothermic, and what we would do is draw a situation where the reactants and the products were in this kind of order, where the products are lower energy than the reactants. Then we look at the actual thing that we're reacting, and since this is primary, then we're going to be going for an SN2 type process. SN2 is a single hump reaction with the activation energy going from the reactants up to the top of the peak. The delta H will be between the reactants and the products. The next thing we want to look at is the nature of the transition state. Now this transition state here is drawn in such a way that the Cn and the Br will be at 180 degrees to each other, and these two H's and this C down here will actually all be in the same plane. The overall shape for this transition state structure is effectively trigonal bipyramidal. When you draw a transition state, what you're drawing is what's going on at the very tip of this peak. And as I've stated earlier, the Cn and the Br are joined simultaneously to the carbon at this point. These bonds are not full bonds, they're partial bonds, but they are 180 degrees apart. To express a transition state, we always use these brackets here and this symbol which indicates a transition state. Alright, so that's the energy diagram, and it's completely labeled. You've got energy on this side and you've got reaction coordinate or reaction pathway on this axis. Over here you'll have the reactants, and it's customary to draw those, and you've got the products down here. This over here represents the mechanism. This is part E. And what we're showing here is that the Cn- is coming in and joining to this C. So the arrow, the tail of the arrow starts at the Cn and the head of the arrow goes to this C. That's the C to which the Br is attached. This arrow starts at the bond and goes on to the Br. Now here's what's important. The fact that the two arrows are in this diagram at the very same time means that those things are happening at the same time. So that's another way of showing that the SN2 is a one-step or a concerted process. Transition state, this here is the mechanism for the reaction, and that's part E. The other possible diagram that you might have to draw is an SN1 diagram. Again, you'll be told whether it's exothermic or endothermic. In this case, it's exothermic, which means the products will be lower energy than the reactants. We're dealing with a tertiary compound here, so we'll be looking at an SN1 type process. SN1s have two humps, with the first hump being very much higher than the second hump. The two humps indicate there's going to be two transition states. Two places where we need to show what's going on at those states. In the first step, the Br is leaving, and we're just dealing strictly with this reactant right here. And the Br is leaving, and we're showing that by drawing a dotted line from the C to the Br. This is not stereochemistry that I'm drawing here. This is showing a partial bond because the Br is just about to leave at this point. And again, since it's a transition state, I put the brackets and the transition state symbol. Transition state 2 has the Cn attaching to a carbocation. The carbocation is not drawn here, it wasn't required, but here's what the carbocation looks like. So when the Br leaves, you're left with this carbocation, which is going to join on to the Cn-. The carbocation is actually right here at the bottom of this little energy well. At this particular point, the Cn is joining on, and the Cn hasn't quite joined yet, but it's dotted. There's a dotted line from the C to the Cn, and that's what's happening at that particular transition state. As the energy gets lower, the Cn joins on completely, and there's your product right there. Again, this has been properly labeled. We've got free energy on this side, or energy, and reaction coordinate and reaction pathway down here. So there are four possibilities that you may have to draw for the test, and these are as follows. You've got your exothermic SN2, and remember you're told whether it's going to be exothermic or endothermic. So this is an exothermic SN2. This is what an endothermic SN2 looks like, where you've got the products at higher energy than the reactants. Your exothermic SN1 looks like this, where you've got the reactants and the products down here, and the endothermic SN1 looks like this, where you've got the reactants here and the products higher. But notice that the general shape of the mechanisms, or the general shape of the energy profiles, remains unchanged.